Last week, we estimate a simple linear regression model where we derived the estimator of beta 1, beta 2. We denoted this as B1, B2. We derived formula for them. And these estimates are kind of point estimate. In addition, we can also do what is called interval estimations. So let's start with an simple examples. Suppose we want to estimate the mean weekly household income. So let Y denotes the weekly household income. Unit is $1,000. We take in natural logarithm forms. So for example, like log Y is equal to 1 is equal to 0 will be equal to log 1. So if the household income is $1,000, and then Y take value of log 1, which is 0. Okay, let's further suppose that we know Y is normally distributed, which means that weekly household income is log normally distributed. With mean mu, we don't know it, but we know that there's a mean there, and variance 1. We assume that we know the variance. This suppose it is 1. Or we can write this, Y is, this symbol says that, okay, Y is distributed as normal distribution, and here is normal distribution with mean mu, variance 1. So we don't know what the mean mu is, and we want to estimate it. That's our task. Okay, a brief note on normal distribution. If Y is normally distributed with mean mu and sigma square, the probability density function is this. And its graph is this. So the bell-shaped curve, the area under this PDF integrate. So integrate over this the PDF over the whole range R, where Y can take values is equal to 1. This is by definition. That's why it means. That's why we call it probability density function. We can also calculate, say, probability of Y less than or equal to 2. So this region is this. So probability Y is less than or equal to 2 is the integrate from negative infinity up to 2 of this density function PDF. Okay. So that's a probability density function. Okay, how can we estimate mu? So intuition will tell we want to estimate the mean, which is average. So intuition will tell us that if we can randomly sample in households from the population, say from Australian populations, it could be 10, 20, 30. Then a sensible estimate of mu is the average of this n household income. So let's estimate that. Simple estimator. So we have household 1, the income is Y1, Y2, Y3 until Yn. We add them up, divided by n. That's what this means. And you know that I'm putting a hat in here. The hat denotes that it's an estimate of the mean. And this is a point estimate. of mu. And we observe that this is random variable. So this is random variable because it depends on data y, and yi is random variables. So this mu hat is the point estimate is an inference about the true unobserved mean of mu. Okay, so we derive an estimated mu hat. Now the question is this estimated mu hat reasonable? The answer is yes. Reasonable means that when what we want to have, we hope to have, if our sample size goes up to infinity, we want this mu hat should converge, should be close to the true value of mu in certain sense. Specifically, we want mu hat to converge to mu in probability, or in other words, the probability that mu hat is far away from the true value of mu is small, eventually converge to 0. And fortunately, we have in probability, we have a result. We have what we call the weak law large number that guarantees that mu hat indeed converge in probability to the unobserved true value of mu as number of observations goes to infinity. So indeed, our estimator works. Okay, suppose we randomly sample the n is equal to 10, and the first household report that 1.1000 and take a log of this 1.1, we get this 0.09531, so on and so forth. Then the point estimate for mu hat is average of all these 10 observations. Okay, and here, and for this particular sample, it is 0.039861. That's a point estimate. This is a point estimate of mu. Okay, in addition to point estimation, we can also do interval estimation, which is an additional tool of the statistical inference. So what is interval estimation? It is a procedure for creating ranges of values, not just one value. So previous a point estimate is one value. So now we are going to create a ranges of values, and sometimes we call this confidence interval, in which the unknown parameters will be likely to be located in this range, in this interval of values. Okay, to do for our little example here, to do the interval estimation, first recognize that estimated mu hat is the sum of in IID independent and normally distributed random variables y1, y2, y3 until yn, y10 actually for our data. So itself, what mu hat is a random variable. Moreover, it is normally distributed. So here is a property of normal distribution. The sum of normally distributed random variables is still normally distributed. Okay, it means we take expectation, we call that mu hat is 1 over n divided by sum of the yi. So taking expectation, we get this. And each mean of EY is equal to mu. So take average of, so we have n sum n, we have sum n mu's. We get n, we sum the mu n times. we get n mu divided by n, we get mu. So indeed, this estimator is unbiased. Okay, the expectation of the mu hat is mu. We can write out the variance, calculate the variance as well. So variance is equal to variance of, this is definition by definition. Okay, for first equality by definition, second equality, we need to impose independency. Assumptions. Remember, our data are identically distributed. And there's a formula for this, but variance. Okay, so you can check if this is not clear to you. You can check our textbook, and we also know that variance of y is equal to 1, because we know that. Okay, so now the third equality is due to identical distribution. So n squared, 1 over n squared times r sum from r to n, and each variance of y is equal to 1. So this term is equal to n. So we get n over n squared, cancel out 1n, we get 1 over n. So mu hat is normally distributed with mean mu variance 1 over n. Okay, given this, we can do the interval. We can do the interval estimation. However, observe that this normal distribution with mean mu and with mean mu and the variance 1 over n is not too good, because this depends on the unknown parameter mu, which we want to estimate, and also depend on data through the n, the sample size here. So let us do some transformation using this trick. I'm going to define a new random variable. Let's call it g, which is mu hat. The old random variable take away from mean divided by standard deviation, which is square root of the variance. And this is just equal to mu hat minus mu divided by 1 over root n, and it's root n times mu hat minus mu. So it's this. Through this transformation, then this g, this random variable, has a standard normal distribution, which means its mean is 0, variance is 1. Okay. You might be wondering why this is the case. This is because of the one property of the standard normal, one property of the normal distributions. If we have a variable is normal, if we have a variable that is normally distributed, we can standardize it. That means we can take away the mean divided by standard deviation, then we get a standard normal distribution, which standard normal distribution means normal distribution with mean 0, variance 1. Okay, that's the graph of the standard normal distribution. Is a bell shape, symmetric around 0, and a variance of 1. So through this, now this standard normal distribution n0, 1 does not depend on unknown parameter or depends on data anymore, and we call this statistics pivotal. So now, by doing this transformation, then we can make probability statement about G, without the need to worry about data. That's why we want to play this trick. So with the standard normal distributions, we can find a constant. This is called TC. So we have this PDF of the standard normal distribution. We want to find a TC. Z here. This is Z. Horizontal axis Z. TC, and this is negative TC. Remember that this distribution, this standard normal distribution, is symmetric around 0. Okay, so we want to find a TC, so that the probability that Z is within this interval from within Z is in this interval is 95%, or the area under of this shaded zone, we want this to be 0.95. Suppose you can choose a different percent, say 0.9, 0.8, whatever. That's up to you. But for my case, I'm going to choose TC, so that this shaded region is 0.95, or we have 95% probability that Z will be located between negative TC to TC. Okay, we can calculate, because this is standard normal distribution, we can calculate, we can through, say, using R or check the statistical tables, we can find that this TC is actually, in the end, we're going to find this TC is 1.96. Okay. So basically what we're doing here is, if we repeat the random sampling of n households by 100 times, then we should find that 95 times G will be located in this interval. Okay, also note that this event, remember G is equal to mu hat minus mu divided by root 1 over n. So doing some algebraic transformation, we can find that this implies this and vice versa. Okay, so these two events are equivalent. So this, and also recall that our task is to estimate the true value of mean, mu, and this is our estimator. So this event says that, okay, mu is located in this interval, mu hat minus TC over divided by root n, mu hat plus TC divided by root n. Okay. And we want this probability of this interval contains the true value of mean to be 95%, 0.95. So we want this. So this interval might contain the true value, and we want this probability of interval containing the true value to be 95.95. So by checking the statistical tables or using the any statistical package like R, for standard normal distribution, we can find TC. This is critical value is 1.96, or the probability of G is between negative 1.96 and 1.96 is 0.95. Then we can write up again. Remember our interval for the true mu is mu hat minus TC divided by root n. From these two, there's one endpoint. The upper endpoint is mu hat plus TC divided by root n. Okay, this endpoint, we know we have know the mu hat, we know the critical value, we know the sample size, which is 10. This is our estimate, mu hat minus 1.96 divided by root 10. We get this. Similarly, for the upper endpoint, we got a 0.659667. So the interval for this sample, or the 95% confidence interval for mu is negative 0.57995 to 0.659667. This is our interval estimations. So these two endpoints provides an interval estimators, and this interval is called the 95% confidence intervals. What does this mean? It means that if we repeat the random sampling of 10 households by 100 times, we should expect to have 95, at least 95 times that the interval estimate will contain the true value of mu, despite we don't really know what the true value of mu is. Okay. Okay, that's a simple examples for this interval estimation. And recall from last week, we estimate these simple linear regression models where we look at the impact of household income on household food consumption expenditure, and we estimate point estimate for beta 2, which captures the marginal impact of income on food expenditure. Is this? That's the formula we derived last time. We can also show that conditional on x. So this says that it's conditional on the data x. B2 is also normally distributed under our assumption SR1 to SR6. Okay, where the mean is beta 2, the true value of the second parameters, with variance of this sigma squared divided by sum of deviation of x from this mean, sum of squared deviation of x from this mean. Okay, and you want to know that we actually don't observe sigma 2, okay, sigma squared. We have data, we can calculate this 1, 2, and we observe it. We have data to calculate n. Okay, we do similar transformation. So take away the mean divided by standard deviation. We standardized the B2. So now let's call this G, and that's standard normally distributed. And I hope now you appreciate why we want to do this transformation. So first, let's suppose we know sigma, okay? Then the 100%. So if we choose alpha to be 0.05, then this would be 95%. Okay, confidence interval for beta 2, the true value of the parameters. Can be computed this first. Find out the critical value. So this is G alpha divided 2 is negative G alpha divided 2. And we want this to be equal to have a probability 1 minus alpha. If alpha is 5%, then this will be 90.95. Okay, we calculate this. From the statistical tables we can find this, because we know now G is standard normally distributed. Then we calculate this. So this implies this. Okay, remember we know this formula for G, so it implies this. And now we know this. We have estimate for this. We know this. We can calculate from data for this. We can get all this. So these two endpoints we can calculate them now. So if we required 50% level of significance, alpha is 5%. The two-sided critical value of the standard normal distribution at 5% level of significance is this negative 1.96, 1.96. So this is 2.5%. This is 2.5% probability. So that this is 95% probability. So we can do the calculation here like this one. So this provide, then this provide an estimate, an interval estimator of beta 2. And how do we interpret this interval and 95% confidence interval? It means that in repeated sampling, 95% of the interval constructed in this way will contain the true value of beta 2, despite we don't know what beta 2 is. And this interval will be based on the assumption the error terms of our simple linear regression model is normally distributed with mean zero variance sigma square. We assume we know this. In practice, we actually don't know what sigma square is, so we need to estimate sigma square as well. So let's now try to estimate sigma square. So this is YI, this is household food expenditure, household 1, household 2 until household n. And this is estimate of beta 1, estimate beta 2, we all know them. And XI is the household income. Okay, so this we know them. Then from there we can calculate the residual and denote this residual as EI hat. So the residual for the first household is E hat 1, second household E hat 2, so on and so forth. Then to estimate sigma squares is just sum of all this square. Okay, we want to first square it because this is square here. Sum of the squared residuals divided by n minus 2. That's one estimator for these variance. Okay, so now remember our z is equal to b minus beta 2 root sigma squared divided by sum of deviation xi squared. So we don't know this. So but now we have a sigma hat square estimate. So what we do is we just plug sigma hat square into here. Okay, so we get t. And we actually can show that this replacing sigma with sigma hat, the corresponding statistics. Now we no longer call it z, we call it t. Is t distribution has a student's t distribution with degree of freedom n minus 2 and its number of observations. Okay. So the statistic t has a student t distribution with n minus 2 degree of freedom. So now if we know sigma, then z is a standard normal distributions. So when we are computing the critical values, then we go to check the statistical table for the standard normal distribution. But now, since we are estimating sigma squares, so the resulting statistics is called t. It's no longer standard normally distributed. Instead, it is t distributed with degree of freedom of n minus 2. So we need to check the statistical table for this t distribution. Okay, so what is a t distribution? It's very similar to normal distributions. So it's also bell-shaped center at 0, so it's center at 0, symmetric around 0. Looks like the standard normal distribution, except it's more spread out, and has a larger variance and thicker tails. And this shape of T distribution is controlled by a single parameter called degree of freedom. So degree of freedom. So in our graph here, the dotted curve. This dotted curve is standard normal distribution. And let's look at the solid red one. So this is a T distribution with the degree of freedom 1. And if we increase to 10, we get a green one. So I hope you agree that it's very, very similar to the standard normal distributions, despite they are different. Okay. So we can find critical value T from a T distribution such that this is the case. So that's the T distribution. We want to find the critical value TC, so that the upper tail, lower tail, the area of this, their probability, okay, to be alpha divided 2. And alpha is something that we can choose. Typically, we can choose alpha to be 1%, 5%, or 10%. Okay. So the critical value TC for the degrees of freedom M is the value this correspond to this. So T1 minus alpha divided 2 M. Okay. Of the T distributions. Consequently, we can make probability statement in terms of T distribution for the confidence interval for beta 2 as this. Here SE is the standard error of B2. Standard error is estimate of standard deviation, and standard deviation is square root of variance. Okay, remember we estimate the variance and we square root it. We call this standard error. So these two quantities, this is lower end point, this is upper end point. They are called 100 times 1 minus alpha percent interval estimate of beta 2. So last week we estimated a simple linear regression model of the food expenditure. So let's now derive a 95% confidence interval for beta 2. We know, let's choose alpha is 5%. We know the sample size, which is 40. Also, we know the point estimate of beta 2 is 10.21. If you don't remember this, you can go back check last week's lecture notes and the codes, the R codes. And we know that variance is 4.38. So we have all the ingredients we need to compute the interval estimator. So the step we want to follow is that determine the critical values. So given that we choose alpha to be 5% and we know the degree of freedom is 38 and the statistics is T distributed, so we can find that the critical value, which is 2.024, then calculate the standard error. So standard error is square root of the estimate of standard deviation, and this we can get it from the OLS regression. So square root 4.38 is 2.09. Then calculate the endpoints of the intervals. The lower endpoint, which is B2, 10.21 minus critical value, so which is 2.024 times the standard error. Then we calculate as 4.97. Similarly for the upper endpoint, 14.45. Therefore, a 95% confidence interval is this, 5.97. to 14.45. Okay, so now you might want to ask, is beta 2 actually in the interval of this? We computed this 95% confidence interval. And the answer is that actually we don't know. And we will never know. However, what we do know is that when the procedure we used is applied to many random samples of data from the same population, then 95% of the interval estimate constructed in this way, using these procedures, will contain the true parameters, true value which is beta 2. So this interval estimation procedure works 95% of the time. What we can say about the interval estimate based on our sample is that given the reliability of the procedures, we would be surprised if beta 2 is not in these intervals. That's how we interpret this result. So what is the usefulness of an interval estimate of beta 2? So this is what we can use it for. When reporting regression results, we always give a point estimate. In our case, in our example here, B2 is 10.21. However, the point estimate alone gives no sense of its reliability. So thus, we might also report an interval estimate. Interval estimates incorporate both the point estimate, the standard error of the estimate, which is a measure of the reliability of our least square estimator. Okay, this is interval estimations.